Hello and welcome to my channel. In this video series, we will be delving into the details of Kaplan turbine design and ultimately constructing our own 100 kilowatt Kaplan hydropower station. First, a bit of a backstory. Almost every light switch in Norway is connected to a waterfall. And I do mean that literally. About 95% of this country's electricity comes from falling water, the highest share in Europe and one of the highest shares on Earth. And it's not a recent green trend either. This is how Norway became a modern country. Wind back to 1890. Norway had no coal, no oil, but we did have mountains, rains, and thousands of waterfalls. If you could turn falling river water into electricity, you could run a factory besides it. And so whole towns grew up around a single waterfall, the most famous one being Rjukan in 1911. The Vemork station switched on, and for a while it was the largest power plant in the world. And behind every one of those plants is a single machine doing the real work, turning water into spin. It's called a turbine. Get it right, and you have unlimited free energy. Get it wrong, and catastrophe will happen. In this video series, we're going to be setting out on a blank page. We will be constructing our own Kaplan hydropower station from scratch, using nothing but free open source software, common knowledge, and a bit of mathematical wizardry. 3 turbines you actually use. There are only really 3 turbines doing the heavy lifting in the world today: Pelton, Francis, and Kaplan. Each one is built for a different kind of water, and the whole game is matching the machine to 2 numbers: how far your water falls and how much there is. Pelton, the punch. First, the Pelton wheel. In Norway, it owns the highest, steepest, and most aggressive waterfalls, because this is exactly what it needs: enormous heights. A Pelton doesn't really use pressure, it works on pure momentum. Take all that fall, squeeze it into a high-speed jet, and fire that jet at a cup on a rim wheel. The water dumps its momentum into the cup and falls away spent. It's essentially a water cannon turning a wheel. This only works with a big enough height to build a jet speed, hundreds and sometimes thousands of meters ahead. The Sima plant in Hardangerfjord runs a Pelton turbine. Its Sima units sit at about 900 meters of fall. Segment 2, Francis, the all-rounder. Second, Francis, the workhorse of Norwegian hydropower and the most common big turbine on the planet. Francis is the middle child. It wants medium head, really anything above 20 meters or so, but swallows far more than a Pelton. Instead of a jet, water spills inwards through a scroll case and guide vanes onto a runner shaped like a curved seashell, running on pressure and flow at once. That is why it's so flexible. A few dozen meters of head up to several hundred. Which is why Norway's biggest, highest output stations are all Francis. Kvidal, the country's largest, is Francis, around 1240 megawatts under roughly 500 meters of head, with Tonstad in the same heavyweight class. Solid head and solid flow. Francis is almost always the winner. Segment 3. Kaplan, the one we're building. Kaplan is what you reach with almost no height but tons of water. A wide lazy river with a small drop. It's the purest of the 3, and relies entirely on pressure and flow. No jet, no mountain. The water pushes through, and a propeller, yes, shaped like a ship's propeller, catches that push. In Norway, you find Kaplans on big, lowland rivers like Glomma, where the drop is 10 or 20 meters, but the river is enormous. Low head, high flow. This is the Kaplan turbine's home turf. Our site is the extreme end of this. 4.8 meters of fall, the height of about a 2-story house, with about 2,500 liters of water flowing per second. That rules Pelton out, and it's even too low for Francis, but it is possible to achieve with a Kaplan turbine. So that's what we built, and here's how to go from the hub out. Segment C1. The hub. Size by physics. Start with the hub, the central cylinder the blades bolt onto. Too small and there is no room for the pitch machinery inside of it. Too big and it blocks the water you came for. The rule of thumb is to put this roughly between 35 to 60% of the blade diameter. This is the circle the tips are sweeping. Ours sweeps at 800 millimeters, and the hub came out at exactly 0.35 meters. 7/16, roughly 0.44. In the low band, but that number is not a guess, it falls out of a hydrodynamic equation. Here's the physics. The hub chokes the flow area, and Bernoulli, the same principle that gives lift to a wing, says squeeze the area and the water speeds up while its pressure drops. That contraction case has its own name, the Venturi effect. Then the blades drop the pressure even further. On the suction side, they make lifts, and at its lowest point, the blade suction side, in the flow past the hub, the local pressure dips towards the vapor pressure of the water. If we cross that line, it will flash boil and lead to cavitation eating the metal. So I size the hub so that the low point lands just above the vapor pressure. The hub's choke alone leaves about 26 kilopascals of headroom. Then the spinning blades stack their suction on top, eating it down to 10 kilopascals final margin. 10 is where we hold the line. I call this deliberate insurance, because warmer summer water raises the vapor pressure and eats headroom. Any pitying on the blades can make its own low pressure hotspots that will seed more cavitation. The hub diameter is a very important choice and something that took a lot of time to get exactly right. Segment C2, the blades, NACA 4 plus a custom twist. Now to the blades, and this is where it gets fun. The cross-section isn't something I invented, it's a NACA 4-digit airfoil, the family of aircraft wings that have been used for a century. Proven, predictable, and not any improvements to be made here. But a Kaplan blade cannot work from one wing at one angle. The tip moves much faster than the root at the same RPM. So the water appears at different speeds and at different angles at every point along the span. If we leave it untwisted, most of the blade would be stalled. The fix: the blade rotates along its length, steep at the hub and shallow at the tip, so every slice meets the flow at the same gentle angle of attack. There is no standard table for our twist, so I wrote an algorithm, feed in the radius, RPM, and local water speed, and it returns the blade angle at every station. The math comes from NACA 4 profiles, but the twist is a completely custom algorithm. Swirl, the secret sauce to low head efficiency. Here's what makes low head Kaplan actually work, and most people have never even heard about this. Swirl. With only 4.8 meters of fall, there is really no energy to waste. So before the water reaches the blade, we deliberately spin it around the machine's axis, the same way the runner turns. That sideways spin is the swirl. The runner's real job now becomes to remove that swirl. Water comes in spinning and leaves straight. The angular momentum you destroyed shows up as torque. On a low head machine, that swirl is your power. Without that, the runner is just a fan in a pipe. Second, regulation. Normally, to throttle the turbine back, you'd add a choke, a valve that restricts the flow of water, but that costs head. You burn pressure along the valve and never get it back. Swirl sidesteps this. Dialing the swirl up changes how much energy the runner pulls out per cubic meter, and it also regulates the amount of axial velocity the water actually has flowing through the tube. So you regulate the machine without physically choking the flow, and the head stays intact. Pitch, the dual duty angle. Last piece on the runner, and this is the one that gets its name, the Kaplan. Almost every Kaplan has a variable pitch blade in the hub, and this is extremely important, because Kaplans are highly sensitive to the angle of attack. This, in our application, does two jobs at once. Job 1. The big swing. Our swing is measured at about 0 to 17 degrees. The big swing matches the swirl. The wicket gate sets how hard the water spins before the runner. Change that spin and the direction of the flow arrives with it. So the blade rotates to follow roughly across the same 0 to 17 degrees as the gates open and close. Job 2, the fine trim. The angle of attack itself, you see the bite that the blade actually takes out of the fluid, has a small, roughly 2 to 5 degrees of freedom. More attack means more lift and more torque. Less attack means the opposite. So as the grid frequency drifts with load, we have a mechanical governor that will just gently tap the pitch to gently follow the 50 Hz frequency. A large swing tracks the angle of the wicket gates, and a small adjustable swing keeps it exactly right with the frequency. This is also highly important in operation because we can set the swirl and pitch independently, and we choose the strategy by season. In the spring, with more water than we can store, we can open the gates. This will slightly decrease efficiency, and we strip the swirl towards the zero, shove as much volume through as we can, but pull more total power while it's there. In the lean season, when efficiency is everything, we add swirl instead, extracting more energy from each cubic meter. We run at slightly higher efficiency but less flow. So we have essentially two different modes from the same machine. The draft tube. Only one piece left, and on a low head machine, maybe the most important one of all, the draft tube. Everything downstream of the blades. Think about the water the instant it leaves the runner. We've stripped out the swirl, dropped the pressure, but it's still moving and heading straight down the axis. All of that speed is energy we haven't captured. Dump it back and you throw it away. And on a 4.8 meter machine, that leftover kinetic energy is a big slice of everything we've got. So we don't dump it. We slow it down gently, behind the runner blades, with a taper that is attached to the hub. As the area opens, the water slows down, and by the same Bernoulli bookkeeping as the hub in reverse, the pressure climbs back up. We're turning leftover speed back into pressure. And here's the payoff. By recovering that pressure downstream, the draft tube pulls the pressure right behind the runner below the water it's draining into. This creates suction, and that suction adds head to what the runner feels. So the blades do more work than the bare 4.8 meter drop should allow. If we get the cone angle just right, gentle enough so that the flow stays attached, this can lead to high efficiency gains. I thank you a lot for watching this lengthy video. If you have any suggestions on how to improve, more information to add, please do let me know in the comments. For those of you more interested in the technical aspect of things, I've linked a presentation to this that I sent forward to the client. It is unfortunately in Norwegian, but I'm sure you'll figure it out. I'm looking to get back to making more videos, and I certainly have a lot of things in mind. So stick around and I'll be sure to upload something in the near future. Thank you a lot for watching.